Hello everyone, I'm Hadi and I'll be the moderator for today's session. We are from Group 4 and we would like to present two topics, standard error and distributions. Our group's presentation will start with the first presenter, Rahmad Noval Baroka, with standard error, the example, and discussion. The second, Indah Harifallah, with standard error of the mean and using Excel to calculate standard error. The third, with me, Muhammad Hadi Dwi Putra, with distributions. The fourth, Mutya Yuliani Anuar, with Pearson's Index of Skewness. The fifth, Muhammad Razak Meizio Maldini Puri, with kurtosis. And the last presenter, or the sixth, Sabrina Dini Hariyanti, with Sebisev's rule, and using SPSS to display histograms. Alright, let's get started with the first presenter.
Alright, thank you Hadi. I'm Rahmad Noval Baroka and the last student number is 22. And now I will explain about the standard error in statistics. So, what is standard error? Standard error is the standard deviations of the sampling distribution of a statistic, usually the mean. It shows how well a sample represents the population mean. If we take one sample, it means only an estimate of the true population. But if we repeatedly take many samples, their means will not be exactly the same, but they will form a distribution. The spread of these means is called standard error. Here we have the example. First, we have the formula. Standard error equals standard deviations divided by square root of n. So we have 4 samples here. Sample 1 have 3 sides, which is 3. Sample 2 we have 6. Sample 3, 12. And sample 4, 18. So we have already got the sample size. And now we need to know the square root of the sample size. So for the sample 1, the sample size is 3. So the square root of 3 is 1.73. And for the sample 2, square root of 6, we have 2.45. And for the sample 3, the square root of 12 is 3.46. And for sample 4, the square root of 18, we have 4.24. So after we got the square root of n, now we apply the formula of standard error, which is the standard deviation divided by square root of n. So for the sample 1, standard deviation for the sample 1 is 4.36 divided by 1.73. So we got the standard error 2.52. And for the sample 2, we have standard deviation 1.97 and the square root of sample 2 is 2.45. So we got 0.81. And for the sample 3, we got the standard error 0.76, and for the sample 4, we got 0.70. So, from the example itself, we have found that the smaller the standard error, the more representative the sample is of the population. Standard error decreases as sample size increases because larger samples tend to produce estimates that are closest to the population value. Therefore, standard error gives an indication of how accurate and reliable the sample mean is compared to the population mean. A smaller standard error indicates a better estimate. That's all from me. Thank you. And for the next topic will be explained by Indah Wuri.
Okay, thank you Gia. Hello everyone, I'm Indah Wuri Harifallah with student number 18. Now I will continue to the next topic. It's standard error of the mean. The standard error of the mean is a measure of how much the sample mean is expected to vary from the true population mean, indicating the precision of the sample mean as an estimate. So it tells how much the sample average would change if took many different samples from the same population. The formula is here. standard error of the mean equal S is the sample standard deviation divided by the square root of n or size of the samples. For sample standard deviation, it has its own formula. It's this. Let's move on to examples. Scores 4, 6, 8. Calculate the standard deviation and standard error of the mean. First, we find the x-bar or the mean. The formula x-bar is equal sum all the x's divided by n. So 4 plus 6 plus 8 divided by 3, we got 18 divided by 3 is 6. So the mean is 6. Now we calculate the sample standard deviation. First, subtract the mean from each data. 4 minus 6 squared plus 6 minus 6 squared plus 8 minus 6 squared equals 4 plus 0 plus 4 equal 8. Now we use the formula S equals square root 1 divided 3 minus 1 times 8. Square root 8 divided 2 is 4. So the square root of 4 is 2. So the sample standard deviation is 2. Continue, calculate the standard error of the mean equals the standard deviation is 2 divided by square root the size of the sample is 3 equal 2 divided by 1.73, then we got 1.15. So the standard error of the mean from this sample data is 1.15. Let's move on to calculate the standard error of the mean on Excel. Now we use Excel to calculate the standard error of the mean. So here is the formula. And we have the raw data here. So to get the standard error, we just type the formula below the data equals bracket because we need to find the standard deviation first. So types the def and open bracket. Select all the data, close bracket, and divide it by bracket because we need find the square root. So type sqrt and open bracket, type count and open bracket again and select all the data again and close bracket 3 times and just click enter. So that's how you get the standard error on Excel. So for the data 2 and the data 3, we just drag like this. And that's it. That's all from me, and the next material will be explained by Hadi Dwi Putra.
Thank you, Indah. Now, with me, I'm Hadi Dwi Putra with last student number 20 or 20, and we move to the next topic about distributions. First, we need to know what a distribution is. A distribution shows how data are spread out. For example, if we flip one coin, we only have two possible outcomes. If it is not heads, then it is tails. Well, if we flip many coins, for example like 100 coins, the results form a pattern. Most results will be around the middle, not at the extreme ends. This pattern creates what we call as a normal distribution, or we can call it a bell-shaped curve. There are some characteristics that we can see from a normal distribution, like the shape. The shape looks like a bell. Most scores are in the center, fewer scores are at the left and right sides, and the mean, median, and mode are equal and located in the center. Now, not all data are normal. Sometimes the distribution is skewed, meaning it is not symmetrical. There are two types. After the normal one, the first, we have negatively skewed distribution or skewed to the left. In this case, most students get high scores and only a few get low scores, and the tail is on the left side. Second, positively skewed distribution or skewed to the right. Here, most students get low scores and only a few get very high scores. The tail is on the right side. In skewed distributions, the mean, median, and mode are not in the same position. They shift depending on the direction of the skewness. Alright, that's all for my part. The next presenter, the fourth, will present about Pearson's index of skewness.
Alright, thank you, Hadi. Now, let's move on to the next material, Pearson Index of Skewness with me. Mutya, Yuliani, and Anuar as the fourth presenter with the last to the number 023. First, let's remember what skewness means. Skewness describes the shape of a distribution, specifically whether the data are symmetric, skewed to the left or skewed to the right. In a perfectly symmetric distribution, the left and the right sides are balanced. Pearson index of skewness helps us measure the value and the sign of the index, and also tells us the direction and degree of skewness using a number instead of relying only on graph. According to Pearson index, if the value is between -1 and +1, the distribution is approximately symmetric. If the value is less than -1, the distribution is negatively skewed or skewed to the left. If the value is greater than +1, the distribution is positively skewed or skewed to the right. So the sign tells us the direction and the size tells us how strong the skewness is. Now let's look at the formula. Pearson's index of skewness is calculated using this formula. Here the x represents the mean, which is the average value, and the median is the middle value of the data. The difference between the mean and the median shows which direction the distribution is leaning. If the mean is greater than the median, the result will be positive, which indicates right skewness. If the mean is smaller than the median, the result will be negative, which indicates left skewness. The number 3 is a constant that helps adjust the scale, and SD is the standard deviation. Dividing by the standard deviation makes the skewness value standardized, so it can be compared across different data sets.
Let's look at a simple example. Suppose the mean is 78, the median is 82, and the standard deviation is 8. If we substitute these values into the formula, we get the mean is 78, the median is 82, and the standard deviation is 8. These three values are all we need to calculate Pearson's index of skewness. The formula for Pearson's index of skewness is P equals 3 times the quantity means minus median divided by the standard deviation. Now we substitute the given values into the formula. At this stage, we are simply replacing the symbols in the formula with the actual numbers from the data. After that, we calculate the value inside the parentheses. 78 minus 82 is minus 4. This negative result already suggests that the distribution may be skewed to the left because the mean is smaller than the median. Now divide the numerators by the standard deviation. The final result, minus 1.5, is the value of Pearson index of skewness. Because the value is minus 1.5 is less than 1, we can conclude that the distribution is negatively skewed or skewed to the left. That's all from me. The next material will be explained by Razak.
Now, let's move to the next material. My name is Razak Meizio Puri, with last data number is 21. I would like to present the kurtosis. What is kurtosis? Kurtosis is a statistical measure that describes the degree of the thickness or flatness of a distribution relative to a normal distribution. In simple terms, kurtosis tells us how high and low the peak of distributions. We have three types of kurtosis. Number one is mesokurtic distributions. Mesokurtic distribution has a kurtosis is only zero. Look like a normal distributions has an inverted moderated peak and moderated tails. Next is leprocotic distributions. Leprocotic distributions has a positive kurtosis like a higher than zero and has a high sharp and very peak. Has heavy tails and indicated more extreme values or antlers. Next is Bicortic distributions. Bicortic distributions has a negative kurtosis, this lowest than zero, has a low and flat peak, has a light tails and fewer extreme values. In mathematical insight, kurtosis is calculated using the four moment of the distributions in practice. Positive kurtosis is a half sharper peak and heavier tails. Negative kurtosis has a flatter peak and lighter tails. And for zero kurtosis are only normal shape. However, the most research we focus more of implementations than the formula itself. And for this formula is delta equal the expected values of x minus mu to the power of 4 divided by sigma to the power of 4 minus 3. And this formula calculated kurtosis using the 4 power of deviation from the mean divided by the 4 power of the standard deviations minus 3. On Excel, we can search kurtosis using this. Kurtosis, equal kurtosis, open parenthesis, B1 to B21, and close parenthesis, or range. And for the example, it is. And for example, using Excel, the kurtosis is calculated with the curve functions. This equal curve, open parenthesis, B B2 to B9, close parenthesis, and enter. And the result is minus 1.2, and which indicated a Pleikurtic distribution because lowest than zero. And that's all from my presentation. And the next material will be explained by Sabrina.
Thank you, Razak, for explaining about courtesies. In this final part, I will explain about Chebyshev rule. But before that, let me introduce myself. My name is Sabrina Dini Hariyanti with the last student number 019. Now, let's move on to Chebyshev's rule and how to display a histogram using SPSS. Chebyshev's rule is a statistical rule that helps us understand how data are distributed around the mean, regardless of the shape of the distribution. This rule can be applied to any type of data distribution, whether the data are normal, skewed, or irregular. According to Chebyshev's rule, at least 75% of the data lie within two standard deviations from the mean. At least 89% of the data lie within 3 standard deviations from the mean. The key phrase here is at least, which means these values represent the minimum percentage. Chebyshev's rule is useful when we cannot assume that the data follow a normal distribution. It provides a basic estimation of how data are spread around the mean, especially in real-world data. To better understand data distribution, Chebyshev's rule is often supported by a histogram. A histogram helps us visually see the spread and shape of the data. Now, I will explain how to display a histogram using SPSS. First, open the SPSS application and prepare your data. Make sure the data have been entered correctly. Next, click Analyze. Choose Descriptive Statistics, and then select Frequencies. After that, choose the variable you want to display, and move it to the Variables box. Then, click Charts. Select Histogram, and check the option Show Normal Curve on Histogram. And finally, click OK, and the histogram will appear in the output view. By using histograms in SPSS, we can visually analyze data distribution and better understand statistical rules such as Chebyshev's rule. That's all from me. Thank you.
Thank you, Sabrina. Alright, since the last speaker has delivered the material, the presentations session has ended. Now, we need to move to the conclusion. First, we have standard error. It is the standard deviation of the sampling distribution of a statistic, usually the mean. There is a formula, and the function is to give an indication of how accurate and reliable the sample mean is compared to the true population mean. A smaller standard error indicates a better estimate. The second, we have standard error of the mean. It is a measure of how much the sample mean is expected to vary from the true population mean, indicating the precision of the sample mean as an estimate. Well, you can see two formulas in here. The left one is for standard error of the mean, and the right one for sample standard deviation. The function is to tell how much the sample average will change if took many different samples from the same population. At the bottom, we can see the Excel to calculate standard error. Next, we have distribution. It shows how data are spread out. In the figure skewed distribution, we can see three types. The first one in the middle is normal, or we can call it as bell-shaped curve. On the right side, we can see negatively skewed, and on the left side, we can see positively skewed. The fourth, we can see Pearson's index of skewness. Skewness describes the shape of a distribution, specifically whether the data are symmetric, skewed to the left or to the right. There is a formula, and the functions are to measure the value and the sign of the index, and to explain the direction and the degree of skewness using a number instead of relying only on graphs. The fifth, we have kurtosis. It is a statistical measure that describes the degree of pickness or flatness of a distribution relative to a normal distribution. There is a formula, and the functions are how concentrated the data are around the mean and how heavy or light the tails of the distribution are. There are three types you can see: platykurtic, mesokurtic, and leptokurtic. And at the bottom, you can see how to use in Excel to calculate kurtosis. And the last material, or the sixth, is Chebyshev's rule. It is a statistical rule that helps us understand how data are distributed around the mean regardless of the shape of the distribution. The function is to provide a basic estimation of how data are spread around the mean, especially in real-world data. At the bottom, we can see the tutorial to using SPSS to display histograms, step by step. Alright, that's all from our group. Thank you for your attention. See you and have a nice day.